Good morning. In this lecture, we discuss about the vector space and some of its example. So vector spaces play a role in many branches of mathematics and its application. In fact, in various practical or theoretical problems, we have a set X whose elements may be vectors in three-dimensional space or sequences of numbers or functions, and these elements can be added and multiplied by constant numbers in a natural way, the result being again an element of Ax. Such concrete situations suggest the concept of a vector space. The definition will involve a general field, but in a function analysis, this general field will be a real or a complex. So first of all, we would like to discuss about what is a field. A field is a set with two operations called addition and multiplication which satisfy the following axioms. There are some axioms under the addition and some axioms under the multiplication. The first we discuss some axioms for the addition. If x and y belongs to be a field f, then x plus y also belongs to be field f. It is said to be closure property. Number two is the commutative property under addition, that is x plus y is equal to be y plus x. And number third is the associative property under addition, which is the x plus y plus z is equal to be x plus y plus z. Number four is the existence of the identity element under addition, that is there exists a 0 in the field f such that a 0 plus x is equal to be x plus 0. And number fifth, the existence of the additive inverse, that is to every x belongs to be f, field f corresponds an element minus x belongs to be field f such that x plus minus of ax is equal to be 0. So now we discuss some of the axioms under the multiplication. So first is the closure property under multiplication, that is x into y belongs to be field f. And second one is the commutative property under the multiplication, that is x into y is equal to be y into x. And third one is the associative property under multiplication. And fourth is the existence of an identity element under multiplication, that is there exists a non-zero element 1 such that 1 into x is equal to be x into 1. And fifth one is the existence of the inverse element under the multiplication, that is there exists an element 1 by x belongs to be field f such that x into 1 by x is equal to be 1, which is equal to be 1 by x into x. And then we have a distributive law, which is the combining the properties of addition and the multiplication, that is x into y plus z is equal to be x into y plus x into z. So for example, we can say that the rational set of a rational number is a field, and the set of rational numbers are satisfying all these of axioms. So now we discuss about what is an algebraic structure. A number system is said to be an algebraic structure if it is closed with respect to be addition and multiplication, that is for every x comma y belongs to be a set A. We have x plus y belongs to be A and x into y belongs to be A. It is closed under addition and closed under multiplication. For example, we have the set of natural numbers under the addition, and under the multiplication again we get a natural number which is an algebraic structure. Set of integers, set of rational numbers, set of real numbers, but a set of irrational numbers are not is not an algebraic structure because it is not closed under addition and the multiplication. Because if we have a under 2 into the minus of a under 2, we have a minus of a 2, which is not a irrational number. So now we discuss about a vector space or a linear space. Let K is a field of a real or complex. A vector space over K is a non-empty set of elements called vectors on X on which two operations, vector addition and scalar multiplication, are being defined, such that the following assertions are true for all x, y, z belongs to be X and R and S belongs to be K. The first one is the closure property under addition that we have already discussed up in a field. And second one is the commutative property under addition. Third is the associative property under addition. And fourth is the existence of the identity element under addition. And fifth one is the existence of an inverse element under addition. And then we have the scalar multiplication will be closed under multiplication. That is r into x, where r is a scalar. R belongs to be a field. Then seventh is the r into x plus seventh and eighth are the distributive properties. R into x plus y is equal to be r x plus ry, or r plus s into the x is equal to be r x plus ry. Ninth one is the distributive and the associative property. The will be there, r into the sx is equal to be rs into the x. And for all x belongs to be x, we have a 1 into x is equal to be x. Now if any set satisfying up all these 10 axioms, then we can say that set is a vector space or a linear space. Now it is a linear space because it's being satisfying of the properties under the addition and the scalar multiplication. So for example, the real over the R, when R is a vector space over the real field, with the vector addition being a usual addition of a real numbers and scalar multiplication being usual multiplication of a real numbers, is a vector space. Similarly, the finite dimensional space, that is R and Euclidean space, we can say is a vector space over R, with the addition and scalar multiplication is being defined as, we consider the vectors, the two tuples x1 to xn and y1 to yn belongs to be Rn. We have, if we go with the addition, the corresponding elements are being added up, and similarly if we go with the scalar multiplication, then we have it is equal to be alpha x1, alpha x2, and so on alpha xn. Similarly, the function space CAB, where CAB will denote the set of a continuous real valued functions on the interval a to b. So let AB belongs to be R and A is less than B. Consider the vector space comprising the functions from a closed interval AB to the field that are continuous on a closed interval A to B, with addition and scalar multiplication are defined as. That is, if f and g belongs to be the function space, then f plus g should also belongs to be a function space. Here is a function defined as the f plus g of ax is equal to be fx plus gx, where x belongs to be a closed interval A to B. And if alpha is then belongs to be a field and f belongs to be a function space, then alpha into f is also belong to a function space defined by alpha into f is equal to be alpha into the fx. The sequence space, now let the sequence space as denote the set of all sequences of a real or complex numbers. Define the operations of addition and scalar multiplication pointwise. For all x is equal to be x1, x2, so on, and y is equal to be y1, y2, so on, belongs to be a sequence space, and all alpha belongs to be the field. Define x plus y as x1 plus y1, comma x2 plus y2, and so on, and alpha x being defined as alpha into x1, alpha into x2, and so on. Then x is a linear space over the field. A sequence space LP. Now LP will denote the set of all sequences of a real or a complex number satisfying the condition that it is a mod summation of modulus of xi power p is less than infinity. Means this series is absolutely convergent. With the addition and multiplication is being defined as follows. It's again a vector space. So if you go to like to prove it out, like say here we have x belongs to be x and y belongs to be LP. So now we have to show that say x plus y belongs to be LP. So here the modulus of a xi plus yi power p is less than equal to be 2 times the maximum of modulus of a xi yi power p, which is further less than equal to be 2 power p maximum of a modulus of a xi power p, comma modulus of a yi power p, by using up the properties of a modulus. So now we know that the maximum of a modulus of xi power p comma modulus of yi power p is definitely less than the sum of the two these xi power p plus yi power p. It means that we have these x plus y belongs to be LP. Also, if x belongs to be a sequence space LP and alpha belongs to be a k, then the summation of a modulus of a alpha into xi power p is equal to be modulus of a alpha p, because alpha doesn't depend upon the I. It comes out of a summation. And we have already the defined LP space which is absolutely convergent, so we can say this is less than infinity. So that is alpha x belongs to be LP. So hence it is a vector space. Similarly, the sequence space L infinity. So L infinity define all the bounded sequence with values in a field. That is the supremum of a modulus of a xi power p is less than infinity. So here the vector addition and multiplication is again defined in the same sense. So it is again a vector space. So L infinity denotes the vector space of all the bounded sequences in the field. Then we have the sequence space, or you can say the convergent sequence space. It will be noted by the letter C. So let C denote the set of all convergent sequences of real or complex numbers. That is, C is the set of all sequences such that the limit xn exists. On the same lines, the previous we have defined up the operations of addition and scalar multiplication will be defined up, and C is a linear space over the field K. And then we happen to be defined the C node. Now here the C node denotes the set of all sequences of real or complex number which converge to 0. That is, the C node is a space of all sequences such that the limit xn converges to be 0. So again, in the like the previous example, we can define the operations of addition and scalar multiplication pointwise, and C node is a linear space over the field K. So in this lecture, we have defined about a vector space and some of its examples. Thank you.